Hello, my name's John Craik. I'm one of the orthopaedic consultants at Epsom St Helier Hospitals, and my talk today is on hip biomechanics. And the idea behind this talk is really to lead up to helping you draw the hip-free body diagram, which you may be asked to do in your exam, and just give you some tips and tricks on how to do this effectively and make sure you get all the points correct. So in order for us to work up to getting drawing a correct hip-free body diagram, we first need to know a little bit about forces, vectors, levers, moments, and force couples. So I'll be going through each of these individually, and then finally be ending on drawing a hip-free body diagram and using that in different scenarios. So first of all, what is a force? So in physics, a force is any interaction that, when unopposed, will change the motion of an object. A force can cause an object with mass to change its velocity, i.e. accelerate. So when a force is applied, that mass will accelerate in the direction of the force applied. And forces have both magnitude and direction, and therefore we can draw these as vectors, which I will go on to describe in a moment. The SI unit for force is the Newton. So Sir Isaac Newton described 3 laws of motion. The first law is that an object either remains at rest or continues to move at constant velocity unless it's acted upon by an external force. And the second law of motion is that the vector sum of the forces on an object is equal to the mass of that object multiplied by the acceleration of the object. So this is the equation of force equals mass times acceleration. The third law of motion is when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. So that's where they're saying for every action there's an equal and opposite reaction comes from. So what is a vector? So a force vector is basically a representation of a force that has both magnitude and direction. And this is opposed to simply just giving the magnitude of the force, which is called a scalar quantity. So these are a couple of examples here of vectors, A, B, and C. And vectors typically represented by an arrow in the direction of the force, and the length of this arrow is proportional to the magnitude of the force. So we can see that the force, the greatest force in this example is force C. So when we look at vectors, it's important to recognise that vectors can be resolved into both horizontal and vertical components if we're looking at a two-dimensional vector. So for example, this vector A can be resolved into both a horizontal component and a vertical component. And the way that we calculate the magnitude of that horizontal and vertical component is through simple trigonometry. So if you remember your GCSE math years, if you know the magnitude or the length of the arrow and the hypotenuse of this triangle, which is A, and we know the angle theta, we can calculate both the horizontal and the vertical components of that force by using sine and cosine. So now we'll move on to describing different types of levers. So levers, basically they're a simple machine which consists of a beam or a rigid rod pivoted at a fixed hinge or fulcrum. And it's basically a mechanical advantage device which trades off force against movement. So if we look at this example here, we've got the person on the left who's applying relatively little effort, but moving a great distance to move a very heavy object. So a lot of force at the other end, but only moving it a small amount. There are 3 different types of levers. We describe first-class levers, second-class levers, and third-class levers. So the first-class lever essentially is a seesaw. So the order of the components of this across the beam are the effort or the forces applied at one end, the fulcrum or the hinges in the middle, and the load is at the other end of the beam. If we look at a second class lever, a good example of this is the nutcracker. So the force is applied at one end, the load is the nut in the middle, and the fulcrum's at the far end. And finally, if you look at the third class lever, this is where the force is applied in the middle, with the fulcrum at one end and the load at the other. And a good example of this is the function of the biceps muscle. So now we're just going to describe moments. So what are moments? Well, moments are about the turning effect produced by a force around a pivot point. And the moment of the force about a point can be calculated as a product of the magnitude of the force and the perpendicular distance from the pivot point. So the point that I've made bold here is the word perpendicular. So that's very important. It has to be perpendicular to the line of action of the force to the pivot point. So the moment equals the force, which is in newtons, multiplied by the perpendicular distance, which is in meters. So therefore the units for moments are the Newton meter. So here's an example of how we can go about calculating moments. So we've got a beam here with a hinge pivot in the middle, and we're applying force W to one end of it. The moment arm in this case is given by the distance D, and that's the distance between the pivot point and the perpendicular, it's perpendicular to the line of action of force W. So the moment in this case is W times D, or WD. Now, if we apply force W in this system, it will result in some rotation of the system about that hinge. But what if we want to maintain a static situation? So we want to maintain equilibrium. So if we now look at maintaining what we call rotational equilibrium, we have to apply a second force in a counterclockwise direction around that pivot point. And if we apply that force at a distance of q, in order for there to be rotational equilibrium, the moment clockwise, which is WD, has to equal the moment anti-clockwise, which is AQ. And we can see that if we maintain rotational equilibrium, the magnitude of the forces in the system are dependent on the lever arm ratio. Okay, and rotational equilibrium is the first step really when we start resolving forces in our free body diagram. However, we've also got to consider that there are forces that may apply some translational effect or cause the mass of this system to accelerate one direction or another. And in order for there to be translational equilibrium, there has to be a reactionary force at the pivot or at the hinge. So for translational equilibrium, we've got to have an upward directed force P at the hinge. And for that for the net force around the system to be zero, that has to be equal in magnitude to A plus W. So to maintain translational equilibrium, A plus W must equal P. And this is the key second step when we talk about our free body diagrams. What happens if we apply a force at an angle that's not in line or not perpendicular to the beam? Well, as we mentioned earlier, we have to calculate the moment, we have to look at the perpendicular distance from the line of action of the force. So here we can draw a dotted line backwards and measure the distance D here, which is perpendicular to that line of action of the force, to calculate the moment. And what about calculating the vertical and the horizontal aspects of force W? Well, we go back to our trigonometry. If we know an angle the force is applied to, we can calculate WH and WV. And again, for there to be translational equilibrium, there has to be reactionary force at the hinge. So in this scenario, the horizontal component of force P must equal the horizontal component of force W, and likewise the vertical component of force P must equal the vertical component of force W. So what's a force couple? Well, this describes a situation where you have two parallel forces that are equal in magnitude but opposite in direction, and they don't share a line of action. So the result is that you actually get pure rotation without translation. And this can also be described as a pure moment. And this is an example here where you have force W applied at both ends of the beam around a pivot point at a distance of D. They're both working in a clockwise direction, and therefore the moment is WD plus WD, so 2WD, and this will cause the system to rotate. However, when we look at translation, we've got W acting in an upwards direction and W acting in a downwards direction. Because they're equal in magnitude, the net translational force is 0, so there's no translation of this system. So now we've been through all that, we can now move on to the free body diagram of the hip. And things we have to recognise about these free body diagrams is that it's a 2D analysis of a hip. It's a very simplified diagram, and it's a static scenario. Because it's static, we have to accept that there is rotational equilibrium and there's also translational equilibrium. And we often analyse these free body diagrams in a single leg stance with applying different aspects to it, such as sticks or walking aids or changing the centre of rotation. And we'll go through all of those. So just to recap, first, when we look at these free body diagrams, the first thing we're going to do is we'll look at the rotational equilibrium. We want the net moments to be 0 and therefore angular acceleration to be 0 because it's a static system. So the body essentially will remain at rest. For translational equilibrium, again, the net forces or translation forces are 0, so acceleration is 0. So that again, the body is remaining at rest. The forces that we have to consider are body weight, the abductor muscle force, the joint reaction force, and the effect of any walking aids or additional loads applied to that free body. And the important thing here is to, what we're wanting to do is to determine what effect these different forces have on the joint reaction force. If we're able to reduce the joint reaction force, for example, in patients with hip arthritis, then that will help reduce the patient's pain due to the force and the pressures within the joint. So that's the idea behind applying walking aids to try and reduce that joint reaction force. So here we've got our hip free body diagram. And we know that the centre of rotation is the centre of the femoral head. Now, the most important thing about this talk that you must take away, and just try and help you getting into any difficulties with drawing these diagrams, is we've got to consider the free body aspect of this diagram. So everything on the pelvic and the body side is what we're looking at. Okay, the forces that we're drawing should all originate from this side of the diagram. Do not start drawing forces around the femur, and this is a common mistake. People may start drawing abductor muscle forces such as this, or ground reaction forces such as this. So remember to stay away from those. Only consider the forces acting on the free body aspect, the pelvic and body side of this system. And these are the two key forces that we begin with. You've got the weight of the patient, which acts around the centre of the mass of the body. And we've got the abductor muscle force, which is given by the vector A. Once we've drawn those forces, the first thing that we have to do is calculate the moment. So we need to know what the moment arms are. And as I mentioned before, this is the distance, the perpendicular distance from the line of action of the force to the centre of rotation of the hip. So here the moment arm for body weight is Q, and the moment arm for the abductor muscle is D. And to maintain rotational equilibrium, the clockwise moments must equal the counterclockwise moments. So AD must equal WQ. So once we've resolved for rotational equilibrium, we can then look at translational equilibrium. First thing we do here is to convert our vector A into both a horizontal and a vertical component. So the forces we have in horizontal direction so far are the horizontal component of A, and in the vertical forces we've got AV, and we add that to W because they are both working in a downward direction. So those are the vertical forces. So to maintain translational equilibrium, we have to have a force acting in an equal and opposite direction. And this is where the joint reaction force comes in. So we need to add both a horizontal joint reaction force and a vertical joint reaction force. To maintain translational equilibrium, the horizontal joint reaction force must be equal to the horizontal component of the abductor muscle force, and the vertical joint reaction force must be equal to the vertical component of the abductor muscle force plus the patient's body weight. And therefore the final joint reaction force vector is given here. And I must stress that the joint reaction force is acting through the center of rotation, or the line of action is through the center of rotation of the hip. And that includes the vertical and horizontal components. So the diagram is not entirely accurate in this regard, but just remember that it is acting through that, line of action is through the center of rotation, so it doesn't carry a moment. So this is our final diagram with the forces around the hip joint. So let's discuss a scenario now where the patient gains weight. So the first thing that happens, we have to acknowledge, is that the force W increases. Force A, as a consequence, has to increase in order to maintain rotational equilibrium. So W is acting in a clockwise direction, A is acting in an anti-clockwise direction, so force A has to increase to maintain rotational equilibrium. The result of this is the joint reaction force has to increase even further. So an increase is not just because of consequence of increase in the downward force W, but it increases also because of the downward component of the vertical component of the abductor muscle force. So both an increase in W and A result in an increase in the joint reaction force. So what happens if we now consider medializing the center of rotation, which has been considered in the past for total hip replacements to improve the wear characteristics of the implants? So if we medialize the center of rotation, as we've done here, essentially we have reduced the moment arm Q, so the moment arm of the body weight, and we've also increased the moment arm of the abductor muscles. We know that the patient's body weight in this scenario has remained unchanged. So what effect does that have on our abductor muscle force? Well, because D has increased and because Q has reduced, the force required by the abductors to maintain rotational equilibrium is in fact reduced. So the result is that reduction in the vertical component of the abductor muscle force also results in a reduction in the joint reaction force. So even though the body weight remains unchanged, there is still a reduction in the joint reaction force because the force required by the abductor muscles to maintain rotational equilibrium has been reduced. How do patients who have hip arthritis help their own symptoms? Well, they may limp and they may translate their body weight more over the affected hip. And the effect that that's having is actually reducing the moment arm of the patient's body weight. And by reducing the moment arm of the patient's body weight, it may then also help reduce the force required of the abductor muscles and therefore also reduce the joint reaction force. What about if we give the patient a stick? Well, the best way to help reduce joint reaction forces is to actually ask the patient to carry the stick in their contralateral hand rather than their ipsilateral hand. And I'll go through both scenarios here. So first thing we have to remember is the stick and the hand that's holding the stick is all part of the free body component of this free body diagram. So it's all on the body side of the hip joint. And what force is applied to this free body from the stick or the hand? Well, there's a superiorly directed or upward directed force that we've denoted as S that's applied either to the hand, or you could say to the bottom of the stick as a ground reaction force there. And it's in an upward direction. The next thing we do is we look at the moments around this system. So we can see that force S is acting in a counterclockwise direction at a distance of B. The moment arm for force S is B, which is perpendicular to the line of action of the force to the distance to the center of rotation. So in this system now, we know that WQ, the clockwise moment, has remained unchanged, but we've now added in another counterclockwise moment, which is SB. And as a result, we know that the abductor moment arm has not changed, but the abductor muscle force can actually reduce to maintain rotational equilibrium. So now we've resolved for rotation, let's look at translation. We know that A has reduced, and therefore the horizontal component, AH, of the abductor muscle force is also reduced, and the vertical component, AV, has also reduced. We've also added in the new force S into the system, and that's acting in an upwards direction opposite to AV and W, and therefore the vertical forces in this system are AV plus W minus S. To maintain the translational equilibrium, therefore, the horizontal component of the joint reaction force must equal AH, which has been reduced by adding a stick, and the vertical component of the joint reaction force has been reduced both by a reduction in A and adding the upward force S. So our joint reaction force has reduced. So this is a scenario that we have without a stick. And when we add the stick, the joint reaction force is reduced because both S is acting in an upward direction and our abductor muscle force has also reduced. So what happens if we give the patient a stick in the ipsilateral hand? Well, so we've added S on the other side of the hip now. Now in this scenario, patients may actually lean more over their hip. In real life, they may lean over more on their hip so they can put more force on the stick. But we're going to consider that they're not doing that and that they're maintaining their pelvis in the same position as before. So first thing we do again is we look at the moment arms and we calculate the moments around the hip. So we've added in a new moment, which is S multiplied by C. But in contrast to having the stick in the other hand, this moment is now acting in a clockwise direction along with the body weight, the moment of WQ. So in order to maintain rotational equilibrium, actually the abductor muscles have to work harder to maintain rotational equilibrium, and therefore force A increases. Then we move on to look at translational equilibrium. We know that A has increased, and therefore AH, the horizontal component of the abductor muscle force, has also increased. And we know that the vertical component of the abductor muscle force has also increased. So although we have added in an upward directed force S into the system, it's not had as beneficial effect as having the stick in the contralateral hand. So the joint reaction force may reduce a little bit by adding the stick, because we've got that upwardly directed force S, but it's not as much as what we saw with the stick in the contralateral hand, because there is an increased force required by the abductor muscles to maintain rotational equilibrium. Now let's consider a scenario where we ask the patient to carry a bag in their ipsilateral hand. So we've now added a downwardly directed force B. Again, the first step we do is we look at the moments around the hip joint. We have a new moment here calculated by B times C, and it's acting in a counterclockwise direction. So the counterclockwise moments are AD plus BC, and they must equal WQ to maintain rotational equilibrium. So actually with this scenario, by carrying a bag, you can actually reduce the force required by the abductor muscles. So force A actually reduces. When we then look to resolve for translational equilibrium, we've got a reduction in the horizontal joint reaction force required because AH is reduced. The vertical component of the abductor muscle force is also reduced, but we now have to consider that we have an additional load of the bag acting vertically in the downward direction, and that is in addition to the body weight of the patient. So actually, although the vertical component of the abductor muscle force is reduced, we still actually may have a gain in the overall joint reaction force, vertical joint reaction force required to maintain translational equilibrium. So although force A reduces, the joint reaction force may still increase. So in summary, we've been through a few examples of drawing hip-free body diagrams. I think the key points to remember are that draw the forces acting on the free body and not elsewhere. So consider the forces acting on the pelvis and body side of the hip joint. Draw the moment arms perpendicular to the line of action of the forces, and first resolve for rotational equilibrium. Then once you've done that, then resolve for translational equilibrium. Thank you very much.